Thank you for joining us. My name is Matteo and I'm part of the new editorial board of Synthesis Workshop. On today's Research Spotlight episode, we invited Sarah French from the George Group. Sarah studied chemistry at the University of Otago, where she achieved her bachelor degree under the supervision of Professor Bill Hawkins. During this time, Sarah approached the synthesis of xanthones and related substances. After that, she started her PhD studies at the University of Adelaide, under the supervision of Professor Jonathan George. Her current research work focuses on the biomimetic synthesis of natural products. I'll leave the stage to Sarah. Welcome, and thank you for joining us today.
Thank you so much for inviting me, and I'm really excited to be able to give my talk. Natural products isolated from the rhizomes of Atrachinenins have been of interest for many years, as these plants have been used as traditional medicines to treat various ailments. So far, the secondary metabolites from these plants have been classified as sesquiterpenes or polyacetylines, but recently 3 meroterpenoids, Atrachinenins A, B, and C, were reported. And these 3 compounds feature an intricate cage-like structure, and the most complex, Atrachinin B, has 7 contiguous stereocenters, which includes a peroxyhemiacetal bridge. We were interested in synthesizing these natural products through a bio-inspired series of cascade reactions, which could explain the racemic nature of these complex molecules. Our proposed biosynthesis begins with a Diels-Alder reaction between a naturally occurring benzoquinone and ocamine. The reaction through an endo-transition state could give the ene-dione bicycle shown here. Then enolization at C5 would provide this enol that could undergo a formal 3+2 cycloaddition to construct the tetracyclic framework present in Atrachinenins A and B. Then the C2 enol could react with triplet oxygen on the convex face to provide a hydroperoxide which could cyclize to give atrachinin B. And finally, reduction of the endoperoxide would lead to atrachinin A. We also proposed the C5 enol could undergo a 2+2 cycloaddition to construct a cyclobutanol intermediate. And similar to a DeMayo reaction, this cyclobutane could cleave by a vanillogous alpha-ketyl rearrangement to give the cyclopentanone, which could react with triplet oxygen to give atrachinin B. Alternatively, the cyclobutane could undergo an oxidative fragmentation to give atrachinin C. Before attempting the total synthesis, we wanted to explore this reactivity in a model system which lacked the geranyl substituent. For our model system, we used a simplified benzoquinone for the Diels-Alder reaction with E-beta-ocamine. The regioselectivity for this reaction is based on frontier molecular orbital theory, and at elevated temperatures, we expected that the preferential overlap of the C3 and terminal methylene atomic orbitals should favor the formation of our desired regioisomer, where the prenyl group is on the same side as the methyl substituents. We found when performing the reaction in toluene, the desired adduct was favoured, however, the yield, reaction rate, and regioselectivity was improved when performing the reaction on water or in a high concentration solution of lithium perchlorate and diethyl ether. The reaction with lithium perchlorate also led to additional side products. So on our model system, we favoured on-water conditions. And now with the ene-dione in hand, we explored various conditions to invoke a formal 3+2 cycloaddition. First, we attempted photochemical conditions, hoping to achieve a 2+2 cycloaddition between the enol and prenyl olefins. When irradiating the compound with UV light in the presence of base, the 3+2 cycloadduct was formed, however, this was amongst a complex mixture. When measuring the absorption spectra of the keto and enolate, we found that in the presence of base, the substrate turned red and absorbed visible light with a maximum absorption around 390 nanometers. Then, using a purple LED with an emission of 405 nanometers, the 3+2 cycloadduct was formed in a 60% yield. DFT calculations performed by the Associate Professor David Huang here at the University of Adelaide showed a concerted 3+2 cycloaddition from the enolate to the cyclopentanone was unlikely, and rather a lower energy pathway by an initial 2+2 cycloaddition, then alpha-ketol rearrangement was energetically feasible. When screening conditions to induce a 3+2 cycloaddition, we found that when treating the Diels-Alder adduct with catalytic amounts of amine bases at elevated temperatures gave the cyclopentanone in moderate yields. However, under these conditions, no intermediates or side products were formed, and DFT calculations were unsuccessful in providing insight into a mechanism to explain this reaction. When exploring the effect of acid and treating the enedione with an excess of CSA, trace quantities of the 3+2 cycloadduct were isolated. Fortunately, reducing the number of equivalents of CSA to 1 mol% gave the desired cycloadduct in moderate yields under a strictly nitrogen atmosphere. In this instance, DFT calculations showed that the lowest energy pathway for this reaction occurs via a concerted 3+2 cycloaddition. However, it was found a stepwise 2+2 cycloaddition, then alpha-ketol rearrangement had a similar activation energy, therefore is a plausible mechanism under these acidic conditions. When treating the Diels-Alder adduct with strong Lewis acids like BF3, a type 1 carbonyl ene cyclization would take place to give this tertiary alcohol. Whereas when treating the enedione with aqueous HCl, a Prinz reaction gave a carbocation intermediate, which could be trapped by the C5-enol to give this cycloadduct. For the 3+2 cycloaddition, we also explored the effect of photoredox catalysis. Using conditions reported by Huang and co-workers, which can support a radical anion intermediate, we isolated a 2+2 cyclobutane along with the 3+2 and a 4+2 cycloadducts, all of which were confirmed by X-ray crystallography. What was surprising is when we performed the control experiments when no photocatalyst was added, some cycloadducts were still formed when irradiated with this blue LED in the presence of base. This suggests that a mechanism involving a radical anion is unlikely and that the blue LED could directly excite the molecule, which we hadn't expected based off the emission spectra previously shown. However, now with the cyclobutane in hand, we could perform the vanillagous alpha-ketol rearrangement to give the cyclopentanone under basic or acidic conditions in good yields. Then moving to complete the oxidation cyclization step with triplet oxygen, the cyclopentanone was treated with potassium tert-butoxide while open to air. Presumably this oxidation occurs through a single electron oxidation of the enolate by triplet oxygen to give an alpha-ketol radical, which can react with superoxide. The peroxide can then cyclize with the C4 carbonyl to establish the peroxyhemiacetal bridge found in atrachininin B. The alpha-hydroxy ketone was also isolated under these conditions. However, we could selectively reduce the endoperoxide with triphenylphosphine to give the analogue of atrachinin A. And not only could the cyclopentanone be oxidized to the analogue of atrachinin B, but we found that when the cyclobutanol was treated with base while open to air, first the alpha-ketol rearrangement would occur, then and the aerobic cyclization gave the analogue of atrachinin B in good yields. And similarly, the enedione could be converted to the peroxyhemiacetal under acidic conditions. When treating the compound with catalytic CSA, first a formal 3+2 cycloaddition could occur, then aerobic cyclization. And finally, we could achieve a one-pot synthesis of the atrachinin B analog from the simplified benzoquinone and E-beta-ocamine. By performing the Diels-Alder reaction at elevated temperatures in toluene, then we could add DABCO to facilitate the 3+2 cycloaddition. Finally, the aerobic oxidation would take place by thoroughly oxygenating the solvent and adding potassium tertbutoxide. Then simply purifying the crude reaction mixture by column chromatography, it gave the atrachinin B analog in 30% as well as the analog of atrachinin A in 8%. And this series of reactions shows exceptional efficiency, as in one pot we were able to construct 4 carbon-carbon bonds and 2 carbon-oxygen bonds and 7 stereocenters. We found when synthesizing the hemiperoxyacetal, it was unstable at elevated temperatures and a significant rearrangement of the scaffold would take place. And to account for the formation of this lactone, we proposed that homolytic cleavage of the endoperoxide would generate a biradical species which could undergo a 1,2 methyl shift, leading to a carboxylic acid intermediate. Then an intramolecular cyclization would lead to the observed lactone, and this rearrangement also occurred when the hemiperoxyacetal was exposed to UV light. We then focused on synthesizing the analog of atrachinin C from the cyclobutane. Using an excess of PETA led to an oxidative fragmentation, which gave the desired tertiary alcohol, which was in equilibrium with the hemiacetal. This hemiacetal was recrystallized and confirmed by X-ray crystallography, and when redissolved, an equilibrium with the diketone was re-established. This equilibrium was not reported for atrachinin C, and we found when comparing the NMR data of our simplified analog, it didn't agree with the reported natural product data. The inconsistencies were centered around the C12 stereocenter, and for the natural product, this stereocenter was assigned based off a nosy correlation between the proton at C12 and proton 6A. However, this correlation is inconclusive as the proton at C12 and 6B are overlapped in the NMR. And so due to the inconsistencies between our synthetic analog and the natural product, and the ambiguity when assigning the stereocenter, we proposed that the atrachinin C was misassigned and is actually the C12 epimer. The revised biosynthesis of atrachinin C could be achieved from this epoxidized enedione, and the C5-enol could open the epoxide to give the tertiary alcohol. We then explored this biosynthesis in a model system and found we could selectively epoxidize the prenyl olefin with MCPBA at room temperature. And this gave the epoxide as an inseparable mixture of diastereomers. Treating both compounds with sodium methoxide led to a complex mixture which contained the revised analog and the previously synthesized epimer along with the hemiacetal. Unfortunately, the revised analog of atrachinin C could be purified from its epimer with careful chromatography. By directly comparing the reported natural product data with both synthetic analogs, we can see the revised analog shows excellent agreement with the reported data, especially at positions 5, 12, and 13, where the proposed analog varied. Then moving to complete the total synthesis of the atrachinins, we first synthesized the alkylated benzoquinone. To do this, ortho-directed alkylation, then oxidative dealkylation with CAN gave the required benzoquinone. For the Diels-Alder reaction with E-beta-ocamine, while on-water conditions were favoured in the model system, Now, using a high concentration of lithium perchlorate and diethyl ether gave the best ratio of the desired adduct to the 3 possible regioisomers. Notably, the presence of the geranyl group did not affect the reactivity at the adjacent alkene, as the major isomers were formed in a 1-to-1 ratio. And also, the isomers where the prenyl is on the same side as the geranyl and methyl substituents were favoured, which is consistent with our model system. And while the desired adduct was synthesized in 36% based off an internal standard, only 24% was isolated as a series of columns on normal, then silver nitrate doped silica were required to purify this complex mixture. And silver nitrate doped silica can aid the separation of compounds which have electron-rich alkenes, so is successful in this case. We then subjected the ene dione to various 3+2 cycloaddition conditions that were developed in the model system. When using thermal conditions with catalytic amounts of DAB-CO, the desired 3+2 cycloadduct was formed in 32% yield. At higher temperatures or with stoichiometric quantities of base, it favoured a sigmatropic rearrangement of the geranyl substituent, but with catalytic loading, we only isolated 12% of this rearranged bicycle. And over extended reaction times, or when resubjecting this geranyl migrated compound, it resulted in the loss of a prenyl substituent and aromatization of the compound. We propose these byproducts are formed following enolization at C5, then a retroclason rearrangement gives an alkylated hydroquinone intermediate. Then a clason rearrangement and tautomerization gives the adduct where the geranyl group has migrated to the C2 position. This compound can then undergo a cope rearrangement to give the retroprenyl moiety, and finally a retro-ene reaction gives the aromatic ring eliminating 2-methyl-2-butene in the process. And further evidence which supported this mechanism was gained when performing the reaction on an allyl substituted analogue. When attempting the 3+2 cycloaddition under photochemical conditions, the sigmatropic rearrangement was observed. When irradiating with light, the C5-enol could be excited to a biradical intermediate as previously seen in the model system. However, now a retroclason rearrangement could occur to give the hydroquinone intermediate, which could react to the isolated byproducts as previously described. And unfortunately, this geranyl migration was also observed under acidic and photoredox conditions. While the sigmatropic rearrangement was undesired, as mentioned, catalytic bases and lower temperatures minimized the alkyl migration and favored 3+2 cycloaddition. Now, with the cyclopentanone in hand, a final aerobic cyclization was required to complete the total synthesis. Treating the cycloadduct with potassium tert-butoxide and DMSO while open to air gave atrachininin B in moderate yields, alongside the rearranged lactone. And we suspect this lactone may be an undiscovered natural product due to the mild nature of this rearrangement from atrachinin B. Finally, atrachinin B could be reduced with an excess of triphenylphosphine to give atrachinin A and complete the total synthesis of these two natural products. And to summarize, we were successful in completing the total synthesis of atrachinins A and B in 6 and 5 steps. Our work in a model system led to the structural reassignment of atrachinin C, and throughout the total synthesis we observed sigmatropic and biradical rearrangements to obtain interesting molecules that could be undiscovered natural products. And before attempting the total synthesis, we extensively studied the chemistry in a model system. For the unusual 3+2 cycloaddition, we suggest this could occur through a concerted mechanism under acidic conditions or by an initial 2+2 cycloaddition, then alpha-ketol rearrangement. We have shown we could synthesize the simplified natural product analogues from a number of substrates, and even developed an efficient one-pot synthesis. Throughout the work in the model system, we observed various side reactions, which led to some interesting compounds. And so with that, thank you all for your attention and for your invitation to present my most recent PhD work.
Thank you, Sarah, for this interesting spotlight on your PhD work, and thank you all for watching. If you enjoyed this episode, you can support our podcast by subscribing to our YouTube channel or Twitter page, and feel free to drop any comment or suggestions. Thanks again for watching, and see you next time.